Hi everybody, this is Jerry Pinter and welcome to Chapter 5 on the Discrete Time Fourier Transform. In this first part of the lecture video, we will be looking at the Discrete Time Fourier Transform for aperiodic signals. Here's a table of contents for this chapter's lecture. Just an initial thought here, this Chapter 5 is basically a clone of Chapter 4. It's almost identical. The only thing that's different, of course, is that we are dealing here with discrete time signals and systems, whereas in Chapter 4 we were dealing with continuous time signals and systems. So the organization of the chapter is almost identical to Chapter 4. So while you're watching these videos, you're going to have some deja vu. You'll be thinking, wow, didn't we just talk about this? And the answer to that question is yes. A lot of the concepts are identical in Chapter 5 compared to Chapter 4. But of course, again, we're going to have to make some adjustments to deal with the fact that our signals and systems in this chapter are discrete time. But you can see that the first four parts here are very similar in organization and structure as what we did in Chapter 4. So in that sense, Chapter 5 is somewhat easier than Chapter 4 because you've already learned a lot of the concepts and theory of Fourier transforms in Chapter 4. So with that in mind, I may go through some of this material a little bit more quickly without all the detailed explanations. The other thing I'll mention here is Part 5, which I may or may not do a video lecture on, is supplemental material, extra credit, and you don't have to do this material at all, but this is where there's a chance to do some extra credit homework assignments on some topics that we're not going to cover in this course. So let's start out by looking at the Fourier transform for aperiodic signals, and of course, again, we're talking about discrete time aperiodic signals. What is the motivation? Why are we, interested in doing the discrete time Fourier transform? Well, again, it's pretty much the same motivation or list of ideas here that we talked about in Chapter 4. This gives us the opportunity to work in the frequency domain. And so one of the advantages there, of course, is that we don't have to do convolution. We can do simple multiplication. We can determine the frequency response of a system using the discrete time Fourier transform. And that frequency response, of course, is a very important function as it tells us how the system behaves at different frequencies. From the frequency response, we can immediately determine the impulse response of the system, going back to the time domain. And from the impulse response, we can determine things like stability of the system. Oftentimes, the most important thing is to find what is the system output. In other words, if we put some input sequence x of n into our system, what is the output of the system? And we're going to be able to figure this out using Fourier transform methods, just like we did in Chapter 4. In Chapter 4, we looked at how to solve linear differential equations, and thus in Chapter 5, we're going to learn how to solve linear difference equations because they describe many discrete time systems. And also, we're going to use these methods and techniques of Fourier transform when we go on to do some of the more important applications of all this signals and systems theory. For example, in Chapter 7, which is on sampling, we will work in the frequency domain quite a bit. And also in Chapter 8, when we get an introduction to communication systems, we will also be working in the frequency domain, and we will be using Fourier transforms. And in particular, or more specifically, for discrete time Fourier transforms, which is the subject of this Chapter 5, it provides a pathway to digital signal processing, or DSP. And this is something that we're really not covering in this course per se, but this is a definite required introduction before you can do more advanced things with DSP, like you might do in grad school, or if you were to take a electrical engineering course on digital signal processing. So this discrete time Fourier transform, which we're going to talk about in Chapter 5, leads to something called the DFT, which is the discrete Fourier transform. And the DFT can be solved very efficiently using something called the fast Fourier transform, or FFT. And the FFT is arguably the most important signal processing algorithm that exists. And this is something that, again, we're not going to cover it in this course, but it is covered in the extra credit activity if you wish to do that. And also things like digital filters and image and audio and video processing are all based on the discrete time Fourier transform. And there again, there are extra credit activities on both of these subjects as well. So for our starting point here, let's compare the continuous time and discrete time Fourier transforms. So in the box here on the left, this is the Fourier transform pair from chapter 4. This is for continuous time. So here is the synthesis equation, and this is the Fourier transform integral here. In other words, this equation here tells us how to calculate the Fourier transform or find the spectrum of the signal x of t. So what we're going to do in chapter 5 is this, in this box here. And basically, if you look at these, they're very similar. So all we're doing here is whenever we see t over here, we replace it with n over here. So this t up there in the exponent, you can see it turns into n here. The other thing is that the continuous time frequency, if we look at the, here we're in this integral here, we're integrating over all frequency, d omega, from negative infinity to positive infinity. Well, remember in discrete time, frequencies don't go from 0 to infinity. They basically just go over 2 pi values, because we talked about this earlier in the course. Discrete time frequencies are technically angles in radians, and once you go around a circle, of course, you're done, right? So we only have to integrate over any 2 pi radian range. So we can go from 0 to 2 pi, or we can go from minus pi to positive pi. The next thing is in this transform integral here in continuous time. Well, remember, here this is time, and time is a continuous variable, so that's why it's integrated here. When we go to discrete time, time, of course, is not continuous anymore. It's discrete, so we can't integrate it. We have to do a sum. So this integral symbol over here is basically replaced with the sum or summation symbol, the sigma notation here. But once we make these changes, these two results here are virtually identical. And so this is, the topic for chapter 5. We're going to be using this Fourier transform pair shown here in the yellow box. So here it is again. This is just a repeat of what I just showed you on the last slide. So this is x of n is given by this, the so-called synthesis equation, or this is also the inverse Fourier transform. In other words, if you know what the Fourier transform is, big X of j omega, you can plug it in this integral and figure out what the signal is in the time domain, what the sequence x of n is. And then this is the Fourier transform definition for discrete time. So what you do is you basically plug in x of n, whatever your signal is here, plug it in this summation, multiply it by e times e to the negative j omega n, and sum it over all n, and that gives you the Fourier transform of x of n, which is called x of j omega. This is also sometimes called the analysis equation, and this also is called the spectrum of the signal or sequence x of n, because as we learned in the last chapter, the Fourier transform here gives us the frequency makeup of the signal. So down here, I'm going to skip over this stuff in the middle here, but basically, what we're doing in this chapter is we're taking a sequence in the time domain, okay, and remember again, of course, this is a discrete time sequence. It might look something like this, and we're taking the Fourier transform to go to the frequency domain, and the Fourier transform, it is a continuous function here of omega. But remember that omega only goes from 0 to 2 pi, and after that it just repeats itself. So we won't always show all these repeats here in the spectrum. A lot of times we just plot it from here, negative pi, to positive pi, or we can plot it from 0 to 2 pi. But anything beyond that is just repeating over and over. Before we go ahead and start with examples and so forth, I just wanted to clarify some notation here that's used that's often confusing. It depends on the textbook that you use, or if you're doing some research by Googling things on the internet and so forth, you'll see different notations for Fourier transforms. So, for example, our textbook for continuous time, a Fourier transform looks like it's always an uppercase letter, and then the argument is j omega. Okay, obviously it's a function of radian frequency omega, but they put this j in there just to remind us that this is a complex quantity, or this function here, this Fourier transform, is a complex valued quantity. In discrete time, your textbook, so for example in chapter 5, uses this notation. X is again the name of the transform, and the argument is e to the j omega. Okay, and later on you'll see this notation as well. X, and the argument is j omega, but the omega is the uppercase omega. All right. Now, why do they use this notation? Well, we'll find out in very soon here when we start doing examples that in discrete time, the Fourier transforms often have factors of e to the j omega in them. Okay, and so that's sort of why they use that as an argument of the function here. However, if you go to other textbooks or other online sources, for example, you'll see that they just call it x of omega, and that makes perfectly good sense too, because remember, this is a function of frequency. And then in discrete, and that would be, for example, for continuous time or for discrete time, they might use that same notation, x of omega or x of uppercase omega. All right, and what I'm using here in my notes for continuous time, I'm using x of j omega, and I'm also using that same notation, x of j omega, for discrete time. Okay, so what is the message here? Well, all of these different forms that are shown here, right, there's like 5 different versions over here on the right. They all mean the exact same thing. Okay, so don't let it confuse you. They're all transforms as a function of frequency. They're just stated in different ways depending on the source and the author of the information. Okay, let's go ahead and move on and start doing some examples. So our first example is the most important example, and this is the Fourier transform of a decaying step function, something that looks like this over here. And the reason that the decaying step function is so important, and why we're going to see it again and again in this course, is because it is the solution to difference equations. And difference equations describe discrete time systems. Okay, so almost all solutions can be represented in terms of these decaying step functions. Now, sometimes the arguments here might be complex, which makes it a little more complicated. But in general, this is an important signal that we're going to want to use. So the mathematical form of this, x of n is the sequence, is equal to some base a raised to the nth power times the step function u of n. And for this chapter here, a has to be less than 1. And I should say that the magnitude of a has to be less than 1. Okay, so a might be 1/2 or 0.9 or something like that. And no matter its value, then this will always be a decaying step function. So to find out the Fourier transform of this sequence right here, all we have to do is plug in this a to the n times u of n into our definition of the Fourier transform, which is this summation right here. So when we do that, this x of n gets replaced by a to the n. Now remember, the step function just means that the signal starts at 0 and only goes to the right. to positive values of n. So what that means is the step function tells us we need to replace these limits of summation from negative infinity to infinity to 0 to infinity, all right, because we're only summing from here onto the right side. So with this in mind, notice that both a to the n and e to the minus j omega n are both raised to the power of n. So what we can do is combine the a with the e to the minus j omega, as I did here, and think of this whole thing in parentheses raised to the n. Okay, so we're just doing a little bit of algebra here. Now the reason for this is that now we can evaluate this summation here using the infinite sum formula, which again is something we explored back in chapter 1 homework. So the infinite sum formula, recall, says that if you have some quantity alpha raised to the nth power, and you're going to sum it from n equals 0 to infinity, then that sum converges to 1 over 1 minus alpha. And this is valid as long as the magnitude of alpha is less than 1. So if we look at, here's our alpha, it's all this stuff inside the parentheses. Well, we know that a is less than 1, and the magnitude of e to the minus j omega is equal to 1, okay, because it falls somewhere on the unit circle. So this quantity in parentheses here, which is our alpha here, is definitely less than 1. So we can use this infinite sum formula, and we can immediately evaluate this expression here. It's equal to 1 over 1 minus alpha, and alpha is the quantity inside the parentheses. So here is our Fourier transform. We're done. This is a Fourier transform for this signal a to the n times the step function. It's 1 over 1 minus a times e to the minus j omega. Okay, so this, and again, we're not going to have to do this, every time we see a decaying step function. Whenever we see a decaying step function that has this form right here, we're going to immediately use this result, and the only thing we have to change is the value of a. All right, so whatever a is up here, we use that value of a down here. And remember, a, of course, has to be less than 1. So what do we do with this result? Well, it's a complex valued function, so we're going to plot the magnitude and phase separately. So let's go ahead and do that next. So here's how we find the magnitude and phase plots for our result on the last slide. So here is our Fourier transform. X of j omega is equal to 1 over 1 minus a times e to the minus j omega. So as you remember, your math teacher told you whenever you have a complex quantity down in the denominator, you have to multiply top and bottom by the complex conjugate. We want to get rid of any complex quantities in the denominator. That's sort of the golden rule of how to handle complex valued functions. So notice, and remember, all we do to find the complex conjugate is we hunt out the j's and we replace them with the opposite of j. So there is a negative j here, so that just flips to a positive j here. And then, of course, we have to multiply top and bottom by the same thing, of course. Now, what happens here is, and it gets worse before it gets better. When we go ahead and FOIL this out on the bottom, all right, we do first outside, inside, and last. We get this quantity here, which you should be able to verify. And now, again, this looks like a mess because now we've got two terms here that are complex quantities. We've got two j's, right? But the good thing is here, they combine. We can use Euler's formula, and let's take this a, which is in front of each of these, and factor it out. So we have e to the j omega plus e to the minus j omega. Well, that's just 2 times cosine of omega, remember, from Euler's formulas. Again, this is stuff going all the way back to chapter 1 now. So this denominator down here on the bottom can be written as 1 plus a squared, that's the real part. I'm sorry, well, that's this first and last term. And then we have minus 2a cosine omega. That's this part in here. And then on the top, likewise, we can use Euler's formula to express e to the j omega in terms of a cosine and a sine. Okay, so again, this thing is looking not any better yet, but we're actually making some progress, because what we can do now is we can break our result into a real part and into an imaginary part. So the real part, remember the denominator now is real. There's no more j's left in the denominator. But in the numerator, we have a j here in front of this sine term. So when we break this expression into real and imaginary, it splits apart as follows, all right? And again, if that's not obvious to you, you should be able to do this out with a piece of scratch paper and see how to work this out. This is just some basic algebra with complex numbers. So let's call this whole real part, all this stuff in parentheses here, let's call it uppercase A. And then we have plus j times all of this stuff, which we'll call uppercase B. So we've expressed our result as A plus JB, all right? So now it looks obviously a lot simpler. And to find the magnitude of this quantity, remember we just used Pythagorean theorem. The magnitude of x is equal to square root of a squared plus b squared. So when you square all this and add it to the square of all of this, it becomes all of this stuff, all right, inside the square root sign, which I won't read. And this all simplifies down to this expression here. 1 over square root of 1 plus a squared minus 2a cosine of omega. And likewise, the phase of j, we can use the inverse tangent function. Remember, x is equal to a plus jb, so that means the angle here, the phase angle, is the inverse tangent of the b term here, which is here, divided by the a term, all right? And remember, this is, a and b are shown here. So again, when you do all this, it boils down to this expression here. So the dust has now settled, and we can plot the results. For the magnitude, which is this function right here, this is what it looks like. This is the Fourier transform magnitude for x of n. It has a peak at 0 radians, all right? And it has a minimum at pi radians. Now remember, 0 is a low frequency, and pi is the highest possible frequency. All right, so basically, this is showing sort of that, it's basically showing a low pass type of, if this was a system, this would be a low pass system because it has the highest value here at low frequencies and the lowest value at high frequencies. And depending on the value of A, that will determine, how high this thing peaks here and how low this low point gets here, but according to this simple relationship shown here. The peak is at 1 over 1 minus a, and that happens when you plug in 0 for cosine here. This just becomes 1 over 1 minus a when you do a little bit of algebra. All right, so I'm not going to discuss the phase right now, but this is basically the transform for that decaying exponential function. So let's go ahead and do some examples using the discrete time Fourier transform. So the first example, suppose we're given the sequence y of n is equal to 5 times 1/2 to the n times u of n. So in order to do this, we're going to take the shortcut in the easiest way possible, and we're just going to use these results that we just derived from a couple slides ago. Remember, we learned how to find the Fourier transform for a decaying exponential function, and it's right here. All right, this is our result. So b is the number out in front. Notice I put that in here, and then a. So in our example, b is 5, and a is the base number that's raised to the n power. So a is obviously equal to 1/2. So we can just take this result right here, plug in b is 5. And plug in a is 1/2, and here's our result. And the other thing I should mention is notice our Fourier transform, we're going to call it uppercase y of j omega because our sequence was lowercase y of n. Here's another one. This time the sequence x of n is equal to -2/3 to the n times the step function. So again, using this result right up here, we see that b is 1. There's a, you can think of a 1 out in front, and a this time is -2/3. So plugging those values in here, we immediately can write the result. X of j omega is 1 over 1 plus 2/3 times e to the minus j omega. So this is how fast this goes now. Now that we have this result here, whenever we see a sequence that is a decaying exponential sequence, we can immediately write our result by inspection. Here are a couple examples of doing an inverse discrete time Fourier transform. So basically here we're going to just work backwards, but we're going to use the same results from before. So suppose we're given a Fourier transform, y of j omega, is equal to 3 over 1 minus 2/7 e to the negative j omega. We're asked to find the sequence, little y of n, that corresponds to this transform. So again, we're just going to use this exact same Fourier transform pair, and by inspection we can see that the b is the number on top, which is 3, and a is the number down here, which is 2/7. And so plugging those in here into this result here, we get y of n is equal to 3 times 2/7 to the n times the step function u of n. Here's one more. This one's just got a little bit more trickier. So in this time we're given the transform x of j omega is equal to 2 over 3 plus e to the minus j omega, and we're asked to find the sequence x of n. Well, the problem here is, if we try to compare this result right here, this Fourier transform, with this over here, we can't do it immediately because we need to have a 1 right here. And notice there's a 3 right here instead. So the trick is we need to get rid of this 3. We need to convert it to a 1. So how do we do that? Well, we divide everything, top and bottom, by 3. All right, and so when we divide the top and bottom by 3, on the top we get 2/3, and on the bottom this 3 becomes a 1, which is what we needed. But remember, we also have to divide this term by 3. So we get a 1/3 out in front of that, but now we can compare this expression here with this result up here, and we see that b is 2/3. We see that a is negative 1/3. Therefore, our sequence x of n must be 2/3 times negative 1/3 raised to the n times the step function u of n. So in the worksheet for this material, you'll be doing examples just like this, where you have to either do the Fourier transform or the inverse Fourier transform by inspection using these results here. So here's an activity for you to try without me, basically. This one is to find the Fourier transform of the delta function, delta of n. So again, here are the Fourier transform pairs. So basically, plug that delta function in where you need to and see if you can come up with a Fourier transform of the delta function. So please go ahead and pause the video and see if you can work this out yourself. All right, so here is the solution to the example or activity where we're trying to find the Fourier transform of a unit impulse. So our signal, our input signal, x of n, is the delta function, delta of n, which, remember, looks like this. It's the simplest sequence known, right? It's just a single value of 1 that sits at n equals 0. So what we're going to do is we're going to take our Fourier transform definition here, and for x of n, we're going to plug in a delta function, delta of n. Now remember what a delta function does. A delta function forces the value of n to be 0, because any other value, the delta function has a value of 0. So it's going to select n equals 0. This is a sampling property of the delta function that we learned back in chapter 1 and 2. So we can set this n over here equal to 0. So this is e to the 0, which is, of course, just 1. We can bring that out in front like this, e to the 0, and that has a value of 1. Now remember the property of the delta function. Whenever you sum over a delta function, you're just adding all these zeros to that 1, and then there's a bunch more zeros. So the sum of a delta function is always equal to 1. So look at our transform. Our Fourier transform, big X of j omega, has the value of 1. All right, for all frequencies. So it's just, it's a very simple transform. It's just a constant value of 1, and this is very similar to what we saw in chapter 4, where we did the same kind of activity. We put the delta function into the Fourier transform definition, and we came up with the same answer. Another thing we can do with the unit impulse is we can represent it as a Fourier transform. And we did this in the continuous time case in chapter 4 as well. So this is very similar to what we did there. So we just saw that if a sequence x of n is equal to a delta function, then the Fourier transform is equal to 1. So let's go kind of backwards. Let's start with the synthesis equation now, which is shown right here. It's this integral here. And let's work backwards. Let's assume that x of n here is our delta function right here. And then we know that the Fourier transform x of j omega is just equal to 1. So you can see I put that in here. So what we have now is an alternate form of the delta function. The delta function, delta of n, can be expressed as 1 over 2 pi times the integral over 2 pi of e to the minus j omega n d omega. And likewise, the delayed delta function has the corresponding shift here in the exponent. So these are useful forms of the delta function because these integrals will show up occasionally. And whenever these integrals show up in a calculation, we can just replace them with this delta function here. So here's a little math exercise for you guys to try. Basically verify that this result is correct. In other words, show that the delta function is equal to 1 over 2 pi times the integral over 2 pi of e to the j omega n d omega. And so do this for both cases. Plug in n equals 0, all right, into this integral here, and do the integral, and see if you get the correct value for the delta function. And then plug in a non-zero value of n, for n here, and see if you get the correct value for the delta function when n is not equal to 0. Okay, so give this a try. Go ahead and pause the video again and see if you can figure this out. This will be good practice for you in handling these integrals here. All right, so real quickly, let's go through the solutions to the activity. So we're supposed to verify that this integral is real, that it basically describes the delta function. So for the first case, when n is equal to 0, well, this is pretty simple. When we put a 0 up here, that just, e to the 0 becomes a 1. So we basically just have an integral of d omega from 0 to 2 pi. Well, the integral of d omega, of course, is omega. So when we go 2 pi, we plug in 2 pi, and then minus 0. And so this, of course, is 2 pi, and we have, remember, out front, 1 over 2 pi. So 2 pi over 2 pi is equal to 1. So basically, we've just proven this right here. We've shown that this integral has a value of 1 when n is 0. Now, the next case is for when n is not equal to 0. So in this case, we're going to leave that n there. But remember, n is an integer. So in order to integrate here, remember when we integrate an exponential function, this is a very fundamental integral. Whatever is in front of the n comes out in front. Whatever is in front of the omega. So we have jn, and that comes out underneath here next to the 2 pi. And we have to evaluate e to the j omega n from 0 to 2 pi. So when we plug in 2 pi for n first, we get e to the j 2 pi n, and then minus e to the 0. Now, these simplify. Remember, let's do the easy one first. E to the 0, of course, is just 1. But e to the j 2 pi n is also equal to 1. Because remember, on the unit circle, 2 pi, or any multiple of 2 pi, in other words, 2 pi, 4 pi, 6 pi, 8 pi, etc., for whatever value of n is here. Well, 2 pi and its multiples are the same angle as 0, because 2 pi means you've gone all the way around the circle and you're back to 0 radians. So this result here is also equal to 1. So what we have here is 1 minus 1, which is, of course, 0. So what we've just proven is that this integral here on the right takes on two values. It has a value of 1 when n is 0, and that's right here, and it has a value of 0 for all other values of n, which are these down here. So therefore, this is equal to the delta function. Here's our last slide of this part of the lecture. This is another example. This is finding the Fourier transform of a discrete time rectangular pulse. And this pulse looks something like this. You can see it has a value of 1, and the pulse goes from negative uppercase N to positive uppercase N. So this is the pulse width from here to here. I guess the pulse width would be 2n plus 1. So our goal is to find the Fourier transform, x of j omega, of this signal here. So what we can see here is that our signal, or our sequence here, has a value of 1 as long as we're in between negative n and n. So that's fairly easy to adjust here. So we take our definition here of the Fourier transform. So x of n here, you can see, can be replaced just by a 1. So we can just, the 1 is invisible there. The only other thing we need to do is we're not going to sum from negative infinity to infinity. We're going to sum from minus n to positive n. So you can see I adjusted the limits of summation there. So let's go ahead and write this thing out for some value of n here. So we have, I'm going to start on, start at the bottom here. So n starts at a negative uppercase n. So I have e to the minus j uppercase n omega. And then we increment. N gets 1, this would be n gets 1 larger, so what happens here is we get minus of n minus 1 in parentheses. And then the next one would be n minus 2, and so forth. And we keep going, depending on what this value of n is, if it's 100 or if it's 3, we keep going, and it'll eventually get to something like e to the minus j2 omega, e to the minus j1 omega, and then this is basically e to the minus j0 omega, which is just e to the 0. And then we get finally to the positive values over here on the right, e to the j omega, e to the j2 omega, e to the j3 omega, and so forth, all the way up to e to the jn omega. Now, what do we do with this? We've got, all these terms. We've got 2n plus 1 terms here. Well, we can make some sense of this by regrouping it. So let's put this is sort of the center point here, because it corresponds to this part of the sequence right here. So let's take our e to the 0 and put it first, and let's pair up this one here, the one on the left, to the first one on the right. So I put those in parentheses there. Then we're going to pair this one here with this one over here. That's the one with the 2's up there in the exponent, and those are shown here. And we keep pairing them until we get all the way to the very end. This one, e to the minus jn omega, and this one, e to the positive jn omega. I put those together here. Now the reason I group them like this is we can simplify this considerably using the Euler identity for the cosine function. Cosine of theta is equal to 1/2 e to the j theta plus e to the minus j theta. So for each of these pairs which are grouped here, we can replace them with a corresponding cosine function. All right. So when the dust settles here, we end up with our Fourier transform. X of j omega is equal to 1, that's the e to the 0, plus 2 times cosine of omega, that's this term right here, plus 2 times cosine of 2 omega, that's this one here, plus 2 times cosine 3 omega, that's the next one, and we keep going until we get to 2 times cosine of n omega, which is represented by this last grouping here. So this is what, and of course, the number of terms here will depend on how big n is up here, how wide this pulse is. This is plotted, this is from your textbook, this example came out of your textbook. This is a plot when n is equal to 2. All right, so there are only 5, total terms here, and if you plot it, it would look something like this. So this is the end of part 1. I'll see you guys shortly in part 2 of this video next. Goodbye.